And so within the vegetable oil, what is actually reacting with the alcohol and so what's going to happen is you're going to have the reaction taking place between the alcohol and you're going to have the alcohol is going to get converted into what's called an ester. And so the molecule in the vegetable oil that is actually participating in the reaction to form the biodiesel, it's going to be the fatty acids. The glycerol does not participate in the reaction to form your biodiesel. It's only the fatty acid part that is actually reacting to form your biodiesel. And so you should have read this document, which includes the procedures. And each of these procedures you're going to view via video, as well as view some pictures of some very important data that you need to write down on your data sheet. So I'm hoping you did your due diligence and you did read this document prior to lab. If you didn't, you may have some difficulty understanding what's going on. So it was very important, and it was stated in eLearn for instructions for this lab to please read this document, including the procedural steps, so that it'll be easier for you to follow along in the videos and understand each step that you are viewing. And so the first part of this lab, as far as the procedures are concerned, is the synthesis of the biodiesel. And so you're going to see two videos. The synthesis was a 2-day process. I did the first part of the synthesis, and then there was a waiting period where I needed to let the mixture sit overnight and settle out into 2 separate layers. One layer is going to be the glycerol layer, the other layer, the biodiesel layer. And so we need to be able to adequately separate those 2 layers. That's why it needed to sit overnight. So you'll watch 2 videos on the synthesis of the biodiesel. And then the next part, part 2, is the separation of the glycerol away from the biodiesel. And then the biodiesel is purified by neutralizing it with the weak acid, acetic acid. After we separate the biodiesel from the glycerol, we'll know the volume of the biodiesel that we made, because when I separated the 2 from each other, I placed them each in a graduated cylinder, and therefore we can read the volume of the biodiesel that we produced. Now, one procedural thing that I had to do a little differently, due to our balances in our lab having a mass limit that they can detect, the big, large 250 milliliter graduated cylinders are too massive to determine their mass on our laboratory balances. So I had to use 2 100 milliliter graduated cylinders to put our biodiesel in. So therefore, when you're determining the volume of biodiesel produced, you're going to have biodiesel in 2 separate graduated cylinders. And so on our data sheet for volume of biodiesel in step 1, you're going to have cylinder 1, and then cylinder 2. They're going to be 2 graduated cylinders with biodiesel. So write down both volumes. But then also in part 3, the analysis, we want to determine the density of our biodiesel. So we're going to need those volumes from cylinder number 1 and cylinder number 2. And then the mass of the biodiesel and the graduated cylinder. You have cylinder number 1 and cylinder number 2. And then you're going to calculate the mass of the biodiesel. And we didn't use 50 milliliter cylinders, we used 100. And we've got 2 of them, so you need to know the empty mass of cylinder number 1 and cylinder number 2. So there'll be pictures for you to get the mass information for each cylinder as empty cylinders for number 1 and for the cylinders plus the biodiesel for number 3. And then to get the mass of the biodiesel, subtract 3 from 1. So again, for number 4, you're going to have a value for cylinder number 1 and cylinder number 2. And then to get the density, is your mass divided by your volume. So you'll calculate two density values, one for the biodiesel in cylinder number 1, density units grams per milliliter, and then for cylinder number 2. And then calculate the average. These should be, if not exactly the same, they should be very similar. And we all should be familiar with how to do an average. Add the 2 together and then divide by 2. So that's a little change to things for part 3A, determining the density. Again, because we produced about 187 total milliliters, so I couldn't put all 187 into a 100 mil cylinder, so I had to split it up into 2 different cylinders. And the reason why I had to use a 100 mil cylinder is because I needed to determine the empty mass of the cylinder. And of course, we have large cylinders in our laboratory that are 250 mil capacity, 500 mil capacity, but they're just too massive in order for our balances to be able to determine their mass. So that's why I had to go with the 100 mil cylinders and use 2 of them in order to accommodate all of the biodiesel that I made. And so make sure that on your data sheet that you, for the density determinations, note that you're working with biodiesel in 2 different cylinders. So that's part 3A. And also you're going to note that for part 2, for the volume of biodiesel that we made, we're going to have biodiesel in 2 different cylinders. And so you'll just write the volume of biodiesel in each of those 2 cylinders. And then you'll write that same information again here under part 3A, question 2. And then the information you need for number 1, you'll get by viewing a picture, by viewing 2 separate pictures. And the same thing for number 3. You'll get that information by viewing 2 separate pictures. And then the rest, 4 and 5, are calculations that you make based on the information that you got from the pictures for questions 1 through 3. Any questions about part 3A on your data sheet? Okay. So if there aren't any questions, I think I have one more thing I need to tell you. Yes. I forgot to take one last picture, and that was the mass of the metal cup after the biodiesel combustion, but I did write that information down. So you won't find this information in a picture or video. I'm just going to give that information to you now. So that's the data for part 3B for the heat of combustion of biodiesel. These other values you'll be able to get from pictures and the videos, as well as performing calculations. And the calculation that you'll perform for line 5, there's a typo here. That should be line 2 minus line 4. And I do believe that's all of the changes or additions that I needed to tell you about. So make sure you go ahead and write down that mass information for line 4 for the heat of combustion determination. And then also make sure you note that for the density determination, that we had 2 100 mil graduated cylinders involved. And so you'll be giving 2 pieces of information in lines 1 through 5 for cylinder 1 and cylinder 2. So now that we've kind of gone over some things, for this week, you'll be just uploading your completed data sheet to the Dropbox. And so for the first video, the first 2 videos you're going to watch are the synthesis of the biodiesel, video 1 and video 2 for part 1. And then I want you to go ahead and move on to part 2. And there'll be a picture of the mixture of glycerol and biodiesel after sitting overnight. And then there'll be a video that'll explain the purification of biodiesel via acid neutralization. And so this video is pertinent for part number 2, separation and purification of biodiesel. you'll get the milliliters of biodiesel in cylinder 1 and cylinder 2. And then the rest of the data that you'll collect is pH data. And so you'll note how many total drops of acetic acid were used to neutralize, and then convert those drops to milliliters, knowing that 20 drops is 1 milliliter. And then from the video, you'll get the starting pH and the final pH. And then there are a few questions for you to answer based on the information you saw in the first two synthesis of biodiesel videos, as well as the separation and purification of biodiesel picture and video. So make sure that you are logged into eLearn, our lab site. And so I'm going to send you to your group meeting rooms. You're going to watch the part 1 videos for synthesis of biodiesel. There's video 1 and video 2. And then you're going to go ahead and watch part 2 video, purification of biodiesel. After you've watched those 3 videos, you will be ready to complete part 2, separation and purification, part of your data sheet, as well as the 3 questions. Once you've done that, you can come back to the general meeting room. We'll discuss your information that you obtained from the video and answer any questions that you have concerning questions 1 through 3. And so let's return to the general meeting room at about 11:50 a.m. after you have watched the synthesis of biodiesel videos 1 and 2 and the neutralization and purification of the biodiesel video. And make sure you filled in your data for part 2, steps 1 through 5, as well as answer questions 1 through 3. And it should take you about 35 minutes to get this part complete. So let's meet back in the general room at about 11:50, somewhere between 11:50 and noon. Are there any questions at this time? If there aren't any questions, you can go ahead and go to eLearn to watch your videos in your group meeting rooms and complete the part 2 of the data sheet. Now that we're back in the general meeting room, the data that we collected for lines 1 through 5, what was the volume of biodiesel in the first graduated cylinder? You should have this written down on your data sheet. You should have watched the video. What is the volume of the biodiesel in the first cylinder? Number 1. Cylinder number 1. I'm not hearing anything back. Can you hear me? Okay, let me go a different direction. Are there any questions about the data that you collected in lines 1 through 5? Are there any questions about questions 1 through 3? Okay, I'm going to assume that there aren't any. And so now that we have neutralized the biodiesel with acetic acid, and of course, acetic acid is an acid. So therefore, if it's neutralizing the biodiesel, we should know from the last chapter, chapter 5, that in a neutralization reaction, that involves an acid and a base. And the products are going to be a salt, which we also call an ionic compound, and water. So question 2 is asking, why did we use acetic acid to neutralize the biodiesel mix? In other words, what were we trying to neutralize? What were we trying to neutralize?
A
And
base.
to answer that question, what was that answer?
A base.
I'm sorry, I can't hear you.
A base. We're trying to neutralize a base.
And what's the name of that base?
I'm not sure.
Did you read this stuff here that you were told to read?
Yeah, I read it.
Okay. So what did we add what did we add to the reaction as a catalyst?
The acetic acid.
No, the acetic acid was not the catalyst to make the biodiesel. Do you see my screen? We reacted the fatty acids and the oil with ethanol. And what did I say that I put in the ethanol? 1 gram of, you just watched the video. You guys should be able to answer these questions if you watched the video. What did I put in the ethanol? Sodium hydroxide. What is sodium hydroxide? That's a strong base. It made the reaction go. If I would have forgotten to add the sodium hydroxide, I would not have made the biodiesel. I definitely wouldn't have made it in 24 hours like I did. It would have taken many, many, many more days. The sodium hydroxide acts as a catalyst. It speeds up the reaction. But once I'm done making my biodiesel, I don't need the sodium hydroxide in my biodiesel anymore. That's why we use the acetic acid to neutralize the reaction. And that was to get rid of the sodium hydroxide. Does that make sense for question 2? So why did we use it to neutralize? We needed to get rid of that sodium hydroxide. And so what the acetic acid did, it reacted with just the sodium hydroxide. And it converted it into a salt and water. Are there any other questions about part 2? Your data that you were supposed to collect in lines 1 through 5 here, as well as questions 1 through 3. Everyone good with that? Okay, so let's move on to the next part of our data sheet. And remember, before we began in my pre-lab little lecture, I told you that I had to use 2 different 100 mil, not 50 mil, but 100 mil graduated cylinders to be able to collect all of the biodiesel that I made. And so I asked this question before, how much biodiesel did I make? How much was in the first graduated cylinder in milliliters? Did you guys watch the video? I'm not understanding why no one's answering my question, why I'm talking to myself. I'm trying to explain the next part. In order for me to do that, I need some feedback from you guys. Come on. I mean, I stated it blatantly in the video, how many milliliters that I had in that first cylinder, how many were in the second. And so, if you didn't watch the video, you need to watch it to find that information. And so you're going to put that same information for volume here in part 3A, question 2. How many milliliters of biodiesel were in that first cylinder? How many milliliters of biodiesel were in the second cylinder? You're going to put that same information for part 3A, for volume of biodiesel. And then what you're going to see, you're going to view some pictures. You're going to view some pictures. One picture is going to give you the mass of the empty graduated cylinders, both cylinder 1 and cylinder 2. So you want to write down that mass that's on the balance in the picture and the pictures that you're going to see. For part 2, again, that's the same volume information for cylinder 1 and cylinder 2, as you should have written down. And I'm assuming no one wrote that down because no one replied to me. So that same information, if you missed that information, you need to go back and watch the video and get that information for volume for cylinder 1 and cylinder 2. You're going to put that same information in part 3A, question 2. And then you're going to view 2 more pictures. That's going to give you the mass of the graduated cylinder plus biodiesel for cylinder 1 and cylinder 2. Write that mass down. And then we want to know exactly how much biodiesel in each cylinder as far as mass in grams. So you're going to for 3, line 3, and subtract from it line 1. So for the first cylinder, the mass here in line 3 will be subtracted from the mass in line 1. Same thing for cylinder 2. To get the mass of biodiesel, you're going to take the mass of this biodiesel plus cylinder and subtract it from the mass of the empty cylinder. And that'll give you the mass of your biodiesel for cylinder 2. And then in line 5 is a density calculation. Density is equal to the mass divided by the volume. So you're going to take your mass in cylinder 1 of biodiesel and divide it by the volume of the biodiesel in cylinder 1. So basically line 4 divided by line 2. You're going to do that for both cylinder 1 and cylinder 2. And then you're going to calculate the average density. Now, the density in cylinder 1 and cylinder 2 should be almost identical, if not identical. So just add those 2 densities together, divide by 2 to get your average density. And then there are questions 1 through 2 to answer. So that's the density determination. The next test that was done is freezing point determination. So there's a video for freezing point determination. You need to fill out this data sheet for time in minutes, the temperature of the biodiesel, and the state of the biodiesel. Is it a solid or is it liquid at that temperature? And so basically you'll see in the video that I added some biodiesel to a test tube, placed that test tube in a mixture of rock salt and ice water, and that's going to cause the biodiesel to freeze. And so we're going to monitor how long it takes for the biodiesel to freeze by checking the temperature every minute, and then note whether or not the biodiesel is in a liquid state or if it's in a solid state. And then we'll determine the exact temperature that the biodiesel freezes. And you'll get that information from the video. And then I took the biodiesel in the test tube out of the rock salt ice mixture and placed it in a test tube at room temperature. And then I monitored the temperature every minute to see when the solid frozen biodiesel would melt. And that would help me determine the melting point of the biodiesel. So I want you to complete those parts, the density determination for part 3A, the freezing point determination for part 3A, and the melting point determination for part 3A. And so you go back to eLearn under the course content tab, and you'll see here part 3, analysis of biodiesel. Click on that little arrow. And then the videos will appear once you click on the little down arrow. Okay. So your first video, well, your first part, the density determination, those are your pictures that you need for the masses of the empty cylinders and then the mass of the cylinders plus biodiesel. So for density determination, you don't have a video, but you've got 4 pictures that you need mass information from. And then once you're done with your density determination, the next you start with your freezing point and then finally your melting point. So you have a video for freezing point, a video for melting point, and then you've got some pictures of the final freezing point curve, the final melting point curve. Then there is a picture with both curves on the same graph. And then I love Excel. So I also did the graphs in Excel. The graphs in the Excel spreadsheet are pretty much the same graphs that you see in the freezing and melting point curves straight from the list. But I like to do things in Excel, so I did the graphs also in Excel. So those graphs will be helpful for you to look at as well. Okay, so go ahead and complete your determination of density of biodiesel under part 3, analysis of biodiesel. Complete the density determination, the freezing point and melting point determinations. And then once you're done watching those videos and viewing those pictures, you are to complete the data for part 3A and the 2 questions, the data for the freezing point and melting point, and then return to the general meeting room. So it's about 12:06. I anticipate you to be done in about 30 minutes. So let's return to the general meeting room at 12:40 p.m.
Professor Cook.
Yes.
So I know part of the reason I didn't answer when you were going over everything is because I personally wasn't able to find the video where you said the amount of biodiesel that you put into the different cylinders, and I've looked all through the eLearn page or the eLearns this week, and I haven't been able to find it. I don't know if somebody else found that.
Okay. Give me 1 second.
I was able to find the pictures of like the mass and stuff, but I wasn't able to find the videos of where you said the volume of each biodiesel in each cylinder.
It wasn't in the synthesis of biodiesel video 2? Okay. Give me 1 second. Did I upload the same video twice? Goodness. Okay. That was the first part. The second part. Okay, give me a minute and I will find that. And when we get back into the general room, I'll direct you to where you need to go. Give me until we meet back in the general room and I will locate that. So I do apologize for that. This lab was a monster lab, and I had to do all this stuff, and I am no videographer by any stretch of anyone's imagination. I had to do all this by myself without anyone helping the video for me or upload any of the videos for me. So I must have missed that video. So please give me a few minutes to try to locate that. That's what it is. I didn't press play on that. So I ended up taking a picture instead of, I think that's what happened. I had it on photo mode instead of video mode. And it only took a picture and it didn't do the video. So the pictures, you could see the volumes pretty well in the pictures of the grad cylinder and biodiesel. Let me Here we are. So can you still see my screen?
Yes, ma'am.
Okay, so this is cylinder number 1. And so that one has 100 milliliters. And then cylinder number 2. That one is 87.
80.
87.
Okay, thank you.
Okay. I see that everyone is in the general meeting room. So does that mean that you have completed both the density determination, the 2 questions? You've also filled out your data sheets for the freezing point determination, as well as the melting point determination? Is everyone ready to move on to the heat of combustion? I'm not getting a response, so I'm going to assume not.
Actually, yeah, sorry, I do have a question. For part 3A, question 2, possible mistakes. So that could be something like messing up measurements or something like that.
Just anything that you saw me do on
Oh,
the
I
video.
see, I see.
Think about if you were me, if you were in the lab as well. Think about some mistakes that can be made that, very normal human error mistakes, like reading the graduated cylinder. Other things, spilling. If I spilled some of the biodiesel, just any little thing that you can think of as far as mistakes that could have been made while doing the procedure for determining the biodiesel. What if I got some of the? What if I didn't drain off all the glycerol? What if I would have mixed some glycerol in with my biodiesel? That wouldn't have been good, wouldn't it? That would have compromised my density determination. And then it would have compromised everything else as well, especially the heat of combustion that we're going to do. So that's one major mistake that one can make, is not accurately and completely separating that glycerol away from the biodiesel. That's a good one there to put for number 2, because that mistake can actually affect your data. If I would not have properly separated out that glycerol from the biodiesel, if I would have came in the next day and just put all of it in one graduated cylinder and I didn't separate out the glycerol, then that would compromise our density determination, our freezing and melting point determinations, as well as our heat of combustion determinations. So that's another mistake that could be made, not separating out the biodiesel away from the glycerol. Does that make sense? Did that answer your question?
Yes, definitely. Thank you.
All right. You're welcome. So what was your density, your average density for the biodiesel that you got? Has anyone determined their densities, both in cylinder 1 and cylinder 2? I just want to kind of check to see what we got. That looks good, Sarah. That's what I was looking for, something between 0.8 and 0.9. Very good, Ewan. Now, does our answer make sense? So when I ask, does our answer make sense? Look at glycerol's density. That's from the literature. Glycerol has a density of 1.26 grams per milliliter. Purified water has a density of 1.00 grams per milliliter. So glycerol is heavier than water. And based on Sarah and Ewan's calculation for the density of biodiesel, glycerol is also a whole lot heavier, a whole lot more dense than our biodiesel. So therefore, it should make sense. It should make sense, perfect sense, that as far as when I went in the next day and separated the biodiesel from the from the glycerol, that the glycerol is the bottom layer because it's heavier. It has the higher density. And the biodiesel with the lower density should have been my top layer. So yes, your density determination of close to 0.9 grams per mil, that makes sense because the biodiesel's density should have been less than that of glycerol because glycerol is heavier. So that's how you would approach answering question 1. Would you be able to identify which layer was which? Yes, by knowing what the density of glycerol is and knowing your density for biodiesel being between 0.8 and 0.9, then yes, by the principle of density, a liquid with the greatest density, if you put them in a column or in a separatory funnel like I did, the higher density liquid should be the bottom layer. The lighter density liquid should be the top layer. So that's how you would answer question 1. Yes, you would be able to identify which layer is which by knowing the densities of the two liquids that make up each layer. So I think you guys have a good handle on the density part, calculating the density and then comparing it to the known density of glycerol. Our density answer makes sense. Us getting a 0.8 to 0.9 gram per milliliter density. And so the next one was your freezing point determination. What did you determine the freezing point to be for the biodiesel? Let's just take a look at our curves here, our graphs. Take a look at the freezing point one first. And so see where the curve starts to flatten out here? That means we're not getting any appreciable change in temperature at the very end. And so that's indicative of a phase change. That means that now all of the liquid is now solid because during a phase change, the temperature does not change. The temperature is always going to be constant during a phase change. So what did you say the freezing point? Sarah said 0.9 degrees Celsius. Sarah is correct. So the freezing point of our biodiesel is 0.9 degrees Celsius. So that means that the biodiesel's freezing point is 0.9 degrees Celsius. And so the next one was the melting point determination. We'll take a look at that graph. And so we see that this curve in the end starts to flatten out and we don't see any significant change. So what did you say your melting point was? So if you said either 14.0 or 14.2, you are correct. I'll accept either one of those, either 14.2 or 14.0. And so in addition to having your freezing and your melting points on your data sheet, you also need to have the data tables completed with the temperature of the biodiesel at each time point, and then state whether or not the biodiesel was a solid or a liquid at that temperature. Any questions about the freezing and melting point determination sections? And again, the volumes, I apologize for that. I had thought that I did a video of the volumes, but it turns out that I wasn't in video mode, I was in picture mode. So all I did was take a picture of it, but you can actually see the volumes while these cylinders are on the scale to determine the mass of the cylinder plus biodiesel. You can also view the volume. And looking at that part up there, the first cylinder was 100 mils, and the second cylinder was 87 milliliters. And so the volume in cylinder 1, 100 milliliters. The volume in cylinder 2, 87.0 milliliters. And then you were to subtract line 3 from line 1 to get the mass of biodiesel in both cylinder 1, and then do that same type of calculation to get the mass of the biodiesel in cylinder 2. And then to calculate your density, just take your mass of biodiesel in line 4, divide it by the volume of the biodiesel from line 2, and that will give you your density. And you calculate your density for both cylinder 1 and cylinder 2, and then add the two together, divide by 2 to get your average. And the average density is, it should be, the density in both cylinders should be very, very similar to each other. And then getting the average, which will give us gives us a better accurate determination of the density by getting the average of the two. And so we're now ready to do the last part, heat of combustion. We talked about heat of combustion in class. So let me just give you the equation. So the mass that we're interested in this equation is the mass of the biodiesel. So we first have to calculate Q. And so what's going to be happening in the video that you'll watch is that you're going to have in a sample cup your biodiesel, and I set it on fire with a match. So it's burning, it's combusting. And then above that sample cup with the combusting biodiesel, there is a soda can that has 100 milliliters of deionized water. So it's pure water with density 1 gram per milliliter. So therefore, if I've got 100 milliliters of pure water, that means the mass is 100 grams. Because the mass is going to be equal to the density times the volume. And if the density is 1 and the volume is 100, then the mass is 100. So I'm going to be heating 100 grams of water by the heat that comes from the combustion of the biodiesel. So we learned about the law of conservation when we looked at the power plant schematic in lecture. That heat is not, the energy is not going to be destroyed from this biodiesel. It's going to be transferred where? To the water in the can. So the water in the can is going to be absorbing the heat released by the combustion of the biodiesel. So we want to know the initial temperature of the water. I do believe it was 21.6 degrees Celsius. And then we let the heat from the combusting biodiesel heat the water up. And then we want to get a final temperature of the water. That's very important. Once we know the final temperature of the water, then we can calculate Q. Q is going to be equal to the mass of the water times the specific heat of water, which we learned in chapter 5 and 6, I think we introduced this. I think we first introduced it in chapter 5, 4.18 joules per gram degree Celsius is the specific heat of water times our delta T. Delta T is T final minus T initial. So first calculate Q, and then use the Q times the mass of the biodiesel to calculate your delta H of combustion, which is the heat of combustion of the biodiesel. But in order to calculate the delta H of combustion, you first have to calculate how much heat did the water receive from the biodiesel. And we're going to assume, using the first law of thermodynamics, that none of our heat is lost, that all of it is transferred to the water. Theoretically, we know that we can say that, but in actuality, some of the heat from the combustion is going to be lost, to the room itself and not directly go to heat the water in the can, but it's a very, very good estimation. And so it's a good assumption to make that all the heat from combustion is being absorbed by that water in the can. So we've got 100 grams of water in the can. We know what our specific heat of our water is. So experimentally, we've got to determine the delta T. We already know what the starting temperature is. So you've got to watch the video to find out what the final temperature is. And when you do, you can calculate your delta T. And when you calculate your delta T, then you can calculate your Q. And then once you calculate your Q, you can find your delta H of combustion. Okay? So that's what you're going to be doing for the final part of the lab. And so you'll be given some pictures in which you will determine the mass of the empty metal cup and then the mass of the metal cup with the biodiesel prior to combustion. And then to find out how much biodiesel in grams that we're using, you subtract line 2 minus line 1. And then after the combustion is over, I forgot to take a picture of that balance with that information, but I did write it down. So you need to write down this information, 48.437 grams. And then to get the change in mass of the metal cup, the change in mass between the before combustion and the after combustion, you take line 2 and you subtract from it line 1, and that'll give you your mass change of the metal cup, and this will give you the mass of biodiesel combusted. And that's going to be the mass that you use to calculate delta H. So we use 100 milliliters. The density of our purified water is 1 gram per milliliter. So the mass of water in our soft drink can was 100 grams. The initial temperature of the water, 21.6. You're going to watch the video and find the final temperature, and then you're going to calculate delta T. And then once you've got your delta T, then you're ready to calculate your Q. Once you calculate your Q, you're going to use that Q and that's going to give you joules. Since we're using the heat of combustion of water, 4.184 joules, instead of using 1 calorie per gram degree Celsius, we're using 4.18 joules per gram degree Celsius. So for your Q is going to be in units of joules, not calories. And then your heat of combustion is going to be in joules per gram instead of calories per gram. And then line 5, that's your mass change in your metal cup, which is equivalent to the mass of the biodiesel that got combusted. So you're going to take your Q value and divide it by the mass in line 5, and that'll give you your delta H. And regular diesel fuel that comes from fossil fuels, it has a heat of combustion of 10,700 calories per gram. For every 1 calorie, there's 4.184 joules. So we cancel out the calories. And that's equivalent to 4.48 times 10 to the 4th joules per gram. So you want to compare your value in joules per gram to the known value for the heat of combustion of fossil fuel diesel in joules per gram and see how they compare. That will let us know whether or not the heat of combustion for biodiesel, is it similar to that for fossil fuel diesel? And if so, then biodiesel can be a logical alternative for fossil fuel diesel. So now I've gone over Some finer points for the last part. Any questions about the heat of combustion calculations that will be required in this last step? If not, go ahead and go to eLearn and watch the heat of combustion videos. There are 2 of them. There's a video 1 and a video 2. But before you do that, check out the pictures. That's the mass of the empty cup without biodiesel, 48.027 grams. And then the mass of the cup with the biodiesel prior to combustion. That's 52.037 grams. And then so to get the mass of the biodiesel prior to combustion, just do your subtraction. So now go ahead and watch those 2 heat of combustion videos. And then finalize all of your calculations for the heat of combustion portion of the lab. And let's meet back in the general meeting room at about 1:30. Madison, to be honest with you, I haven't had a chance to make the Dropbox yet. I was in the lab last night until about 8 o'clock finishing this lab. Then I got up at 6 a.m. this morning to process all the videos and get them ready for 11 a.m. And that's the one last thing that I need to do is actually make the Dropbox. So you will see it. I will make it right now. Okay. That's the one last thing on my list that I need to do for this lab. Okay, so you should have completed watching the 2 heat of combustion videos, and you should have the following data and calculations done. The calculations in lines 1 through 11 are really simple, nothing harder than subtracting. So like in line 3, to get line 3, you just take line 2 minus line 1. You should have got about 4.01 grams. And then line 5, you get by taking line 2 and subtracting from it line 4. I gave you this information for line 4. And then that's the mass change in the metal cup. And what that means is that's the amount in grams of the biodiesel that actually got combusted. So we had a total of 4.01 grams of biodiesel. So what that is telling us, not all of the biodiesel combusted. A little bit of it didn't, which is to be expected. And as the video stated, I added 100 milliliters of deionized water, which has a density of 1 gram per milliliter. So that means I added 100 grams of water to my soft drink can. The water in the can started out at a temp of 21.6. The final temperature, 89.1. So therefore, we take 89.1 minus 21.6, and that gives us our delta T. So there's our delta T. So our temperature changed by 67.5 degrees. So now we can use that delta T to calculate Q. And then once we calculate the Q, then we can calculate the delta H, the heat of combustion. It's going to be equal to Q divided by the mass of biodiesel that combusted. Which is shown in line 5. And then once you get the heat of combustion, then you compare it to the heat of combustion of fossil fuel diesel, which is 10,700 calories per gram, or 4.48 times 10 to the 4th joules per gram. And so if you calculated your Q and your delta H in calories, then you want to compare your delta H that you calculated in calories to this value. Or if you calculated in joules, then you want to compare your heat of combustion in joules per gram to this one. We've been working more with joules as far as an energy unit in the lecture. So I would take either answer, your Q in calories or either your Q in joules, your delta H of combustion in calories per gram or joules per gram. And then talk about in question 14, is your calculated heat of combustion for the biodiesel Is it similar to the heat of combustion for fossil fuel diesel? And that is it. And so once you have your lab complete, you can upload it to the Dropbox, which is available. And there's your Dropbox for submission of your biodiesel lab. Are there any questions about combustion of biodiesel part of our lab? Well, if there aren't any additional questions, you are free to leave the meeting room, or if you are still working, you are free to stay in the meeting room and finish up your calculations. And just remember to upload your lab report form to the Dropbox by tomorrow night.
Do we need to upload those few pre-lab questions that were
No.
on the?
No, just the lab report form.
Okay, thank